Okay. Right. Good afternoon. Right. So last time we start doing operating systems and we finished file handling and also we did some past paper questions. So today we move on to our second subtopic. We have three subtopics, right? File handling, process handling, memory handling, right? So today we want to finish process handling or the process management. So again, the note is available in your Google Classroom under operating systems. Okay. Right. So let's do it. It's a small topic, but very important topic for exam. Again, you get MCQs and structured questions in some years. Okay. Right. So remember the key task of operating systems are operating system is managing software, which includes install, uninstall, upgrade, as well as running programs. So that is also part of the uh, task of operating system other than managing hardware and security and so on. So this is managing software. So remember when we say manage software, operating system facilitate you to install, uninstall, upgrade. Okay. But that is one aspect. Second aspect is operating system run programs. So what is a process? Process is the running program. When a program is run, we call it there's a process. Okay, there's a process. So why does operating system need to manage processes? Because computer is a multitasking environment. So we don't buy a computer to do one task or run one program. We buy a computer to run different programs at different times or sometimes at the same time. Right? For example, right now in my laptop, PowerPoint program is running. Zoom software is running. So this software that I use to draw in the screen, that is also running. And there are some other programs running in the background, like the Google Chrome is running. Okay. So all these running programs are called what? Processors. So if you want to look at what are the currently running programs in your computer, if you have Windows, go to Task Manager. And these are the processors running. Okay. And you can see how much of resources are currently allocated by OS for those, right? Zoom use 5.9 of the percent CPU and about 400 megabyte of memory and so on, right? So you can see different programs. Firefox is there because I'm running Firefox right now. Okay. The PowerPoint is there, right? So what we discuss is about this. This is done by operating system. Okay. Right. So what is a process? Process is a running program. And processors are under the control of operating system. Okay. Right. How does process get start? So that is simple answer, but you must know. Even the examiners have asked that. There are different ways. One way is a particular user run a program. So at any time I can say I want to run Word. I want to run Photoshop. So either using command line or using menus, you run a program. So there's a second way of running a program. That is, you can schedule the program to start. So there's in any operating system, there are schedulers. In Windows also, there's a scheduler. Right? So you go there and say, what is the program, in which day, which time you want to run it. Or you can specify each day, this time. Once a week, this time. This day, this time. So then when that particular time date set is, your operating system will run that program. So that is the second way of running a program. Schedule tasks, schedule jobs. Right? The third way is one program can start another program. So that is also possible. And of course, when we say scheduling tasks, there are some programs automatically start it when you start up your operating system. That is also sort of a schedule. So that means when operating system starts, automatically that program runs. Of course, you can stop it, but it automatically auto run. So those are the possibilities for running a program, getting a process. Okay. So then how can we get it terminated? Running program get terminated. One possibility is that program naturally terminated because your task is done. So there can be that kind of situations. Maybe you have scheduled to download, and after the download is done, the program can close itself, terminate itself. Or user can close or exit the program. For example, at any time, I can close this software. I can close Zoom. I can close PowerPoint. So then again terminate. The third possibility is operating system will decide to terminate the program. Maybe it detects an error, resource conflict, security issue, and so on. So in that case, OS will terminate it. And sometimes it will give you error message or put a log entry giving the reason why it was terminated. Okay. Right. So those are the three possibilities. Program naturally complete its task, user close it, or operating system terminate it due to errors, exceptions, conflicts, and so on. Right. I already explained you why do we need process management. So we need process management because modern computers, including your smartphones, servers, they are multi-user multitasking. So in multi-user multitasking, yes, we need OSs, especially to manage processors, giving them the hardware resources. Otherwise, one process will take all the resources, prevent conflicting situations, prevent security issues. One process accessing resources of another process, one process accessing data of another process. So therefore, operating system tightly control it. Okay. Right. So I use the word multi-user multitasking. Remember, we classified operating systems in the very first day. Single user, single task, single user multitask, then multi-user multitask, and real-time operating system. So modern OSs are pretty much either single user multitask or multi-user multitask, like Windows, Linux, Mac. So that means multiple programs can run at the same time, which is somewhat complicated situation. And not only that, in some operating systems like Linux, multiple users can use the computer at the same time and they can run multiple programs. So then forget about the multi-user. What about multi-task or multi-process? So that means parallelly different programs are running. For example, right now Zoom is running, PowerPoint is running, Firefox is running, and so on. So how does it happen? You know that even humans are capable of multitasking, right? We can do multitasking. For example, while I'm drawing certain things, I talk. So while you eat, right, maybe you can talk to someone, watch television, So we can do certain level of multitasking. But how do we do multitasking? So basically how we do is we give short attention to different tasks. Give attention to this, then immediately give this attention to this task and that task, and so on. So the OS does the same thing. Assume that you have single processor. Single processor. That means just one processor. Remember, the main component that run the program is processor. Other hardware is to help store and so on. It is a processor that run your program. If you have only one processor, you know that at a time only one program can be run. So if you have only one processor, how do you do multitasking? Running multiple processors. The simple answer is your operating system break the time into small time slots, and different programs are given different time slots. Those are so tiny in millisecond level. So therefore, we feel like multiple programs are running, but in reality, bit of this is running, bit of this is running, bit of this is running. Right? So then again, attention given to this, attention given to this, and so on. When it happens so quickly, we feel like all these programs are running, but actually, at a time, only one program or process is running. So that is called context switching. Operating system can switch the context frequently in millisecond levels, right? Giving context to this, again, this. So therefore, we feel like gradually all these programs are proceeding. Got it? Doing bit of different tasks, but at a time only one task. Right. So then if you have multiprocessors, like you have multiple processors, that means physically there are more than one processor in your motherboard, which is very rare anyway. So this is usually available in servers, server computers, which need a lot of processing power, like web servers, database servers. So then, of course, different programs can be run by different processors. Maybe process one is handled by processor one, other process or process two is handled by processor two. Maybe process 135 handled by processor one, process 246 handled by this. So workload can be shared because we have physical processors. But that is not usually the case in our day-to-day laptops, smartphones. But anyway, there is possibility, right? Of course, multiple computers are there. Another option is you have one processor, physically one processor chip in the motherboard, but that one processor can behave logically as multiple cores, right? Dual core, that means two cores, octa core, eight cores, quad core, four cores. That is one processor chip, but that processor chip behave like two processors, four processors, eight processors, but not separate process. But actually, it's like physical process, though it is not separate. So that is multi-core. Then again, different processors for running programs can be handled by different cores. Different cores. So we call it logical process. Multiprocessor means multiple physical processors. So then there's another concept called multi-threading. Your programs can, a particular program can be run as multiple threads. That also gives a bit of a parallel processing nature. So all these things, of course, at hardware level, you need multiple processors and multi-cores. But context switching, multi-threading is handled by operating system. And of course, if you have multiple processors or multi-cores, again, operating system must take care of these things. So operating system will detect that we have multiple processors, your processor has multi-cores, and your operating system will utilize it. So I told you in the very first day, when it comes to software, the most complicated software engineers have ever made is no doubt operating systems. It's not inventory management systems or accounting systems or Photoshop or Word or whatever, or Instagram or TikTok. The most complicated software man has ever made is operating system because it manage hardware, it manage programs, overall control, manage security. So now you can see how tough task it is, right? That is why we have only few operating systems in this world, right? So, so Linux variations, Windows, Mac OS, when it comes to mobile, Android and iOS, and so on. Right. So if you want to get a feeling of these things, again, you can go to Task Manager and go to Performance. And this is how much of memory is used. Anyway, our next topic is memory management. We will come back to this later, next class. So now you can see here CPU. So this is the current CPU usage. I have 2.8 gigahertz i7 processor, okay, 11 generation processor. And you can see currently it utilize about 20%. 20%. But if you go down, you can see, so it has one processor, but four cores. I don't know whether you can see it. Four cores are there. Right? Four cores are there. That means four physical processors inside my processor, but not set only one chip, but it act like four processors. Okay. And it behave like eight logical processors. My four physical processors behave like each physical processor behave like two logical processors. So that is why four cores, eight logical processors. Okay. And here you can see how many threads are running. So remember, multi-threading is also there. Right now, 3,730 odd processor threads are running. Okay. And of course, I have a separate GPU, graphical processing unit, because my CPU is concentrating on general processing, whereas GPU concentrate on graphic related things. Especially now we are running a Zoom session. So bulk of that burden is taken by GPU. Okay. You can see video processing, 3 dimension, right, and so on. Okay. So make sure you go there and practically feel it, right? Rather than just memorizing things. Okay. Right. So therefore, modern computers are not single processor. Even though it is a single processor, it has multi-cores, multiple logical processors, multi-threading, and in some cases, even we have multi-processors. But whatever the approach, still context switching is used. Even though you have four cores, eight logical processors, at a time, definitely more than eight programs are running. Maybe 20 odd programs are running. So therefore, still context switching is used. Context switching is used. Even though you have so many cores, still context switching is used. Not only in single processor, but in exam papers, to make your life easy, most of the time examiner will say it's a single processor computer. So then you don't need to think about any other complications. But that is to just to make your life easier and make your questions easier. Okay. But even though it is not single processor, you can forget about other things and just concentrate on context switching. Okay. So we'll do a past paper question if we have time today. Right. So what is the most important concept for us? Context switching. Switch the context. Context means to which program you give the attention, always give attention. Currently concentrating, currently giving attention. So how the operating systems do multitasking? It periodically allocates small time slot for each running process. So time slot are given. Maybe processor 1 is given, processor 2, processor 3, process 4, process is running program. Maybe again attention given to process 1, process 2, and this can change. Maybe after process 2, maybe process 4, or maybe process 5, and maybe then process 3. So there's no guarantee that it's always give the same order. So there can be some changes, but in general, it try to give sort of equal opportunity. But again, there's a concept called process priorities. So if you have running a high priority process, operating system will give more time slots or more frequently that those processors will be called, right? So even you can look at those things also if you go to task manager. And if you go to the services, sorry, not services. Right, so here you can see this is details. Process ID, these are the running programs, so processors. You can see Zoom is there, Firefox is there, Google Cloud Service is there, okay? Uh, so it says whether it's running. Most of the time what you see is running, but very quick burst, it goes into other states also. But you feel like everything is running, but actually uh, sometimes in a very short period, it goes into idle and so on, okay? And the other thing is, if you right click, there's something called set priority. So by default, it is normal, but if you want, you can give it high priority or even real time. But usually we don't change it. And also when we run a program, we can set the priority at the program runtimes also. But in general, usually we give, or the operating system give the same normal priority to each and every program. But you can at any time change it. That means more time slots will be given. Or you can configure so that when you run a program, it starts with a high priority. So that means more attention, more time slots. Okay. But in general, operating system will try to give sort of equal attention. But if a particular program needs more processing power, it will be given more time slots so that effectively end user will feel like all the programs are running. Okay. That is the idea. So there are algorithms to decide that what percentage of time slots are given to which program or process. Okay. It's like a mother giving attention to the kids. So if there's a one particular kid who need little bit more attention, of course, mother need to give little bit more attention. But at the same time, mother will make sure that everyone get the attention. Okay. Maybe a particular kid is not well. So likewise, there can be situations in running programs also where you need more attention. So then operating system will dynamically decide those. Right. So that approach is called what? Context switching. Right. So now you must know what are the process states. This is the most important slide. Because remember, at a time, there can be multiple programs running. But it doesn't mean that every program is in the same state. I told you when I look at the running processes, it looks like every program is in the running state actually. If you go to the task manager, so details, so you can see you may sometimes get fooled that okay, every program is running. But in reality, not every program, you can see some programs are suspended. I just order by status. But though here we say those are running, actually those also move into different states and come back to running. But most of the time it is in running. That is why you feel it like running. Okay. You feel it like running. Okay. Right. Right. What are the possible processor states or process state? When you start a program, either you start the operating system start at startup, operating system started because it's a scheduled task and then now the correct date and time has reached, or you just start it by click on that door running from command line. So it goes to what is known as new state, right? So operating system identify that program as new state program or new state process. New state doesn't mean now it is being run. No, it's in new state. Okay. So if there are so many programs waiting to be run, sometimes your process or the running program will be in the new state for some time. That is why sometimes when you run a program, it takes a bit of time for it to appear at least. That means operating system has kept it in the new state because operating system is too busy or too many programs waiting in the new state or too many programs are running. So then there will be a small delay. Uh, your OS will until the OS start running it. So that until that time, we say that your OS is so your process is in the new state. So then operating system will admit the new state process into ready state. So we call use the word admit, like admitting a patient. Okay. So that means after some time, so maybe within few milliseconds, or sometimes maybe within after few seconds, your new process is now in the ready state. Again, ready state doesn't mean now it is running. No, it is ready to run now. It is ready to run. In new state, it is not ready to run. It is waiting in the queue. But this is now admitted, like a patient admitted to the hospital. But it doesn't mean that the patient is getting the treatment, but get ready to get in the treatment. Just think of as analogy. Right. So then not only your process, maybe some other processes are in the ready state. Sometimes maybe 5, 6 processes are in the ready queue. So then remember operating systems give time slots to processors. So when operating system give a time slot to a particular process, so we say that it is now not in the ready state, it has moved to the running state. So we say that the process has been dispatched to running state. So earlier it was in ready state, now running state. But that running state, it will be there for very small period, maybe few milliseconds. Because operating system need to give attention to other processes also, take other processes also into running state. So then after few milliseconds, again, your running state process will go back to the ready state and stay in the bench waiting again. So when the time slot is over, time out, now the process is back in the ready state. Not only one process, there can be multiple processes in the ready state. But at a time, if you have only one processor, one core, only one process is in the running state. But if you have multiple processors, multiple cores, multiple processors will be in the running state as well. But for the exam, most of the time you can assume that it's single processor. So at a time, only one program is in the running state, and many programs are in the ready state. So it can move between ready and running many times because you are back in the ready state because your timeout, and again you get a time slot. Always give you a time slot back in the running, and again program runs another bit of portion. Again timeout and getting back to the ready. Again your program get the attention. Again running. So it keep happening. So this is the main state transition. Going to the running, back to the ready. Going to the running, back to the ready. Sometimes hundreds and thousands of the time program can go through this cycle. Okay. So then when your program is done, now it's getting the time slots, attention. Maybe after few time slots, maybe 1,000 time slots. Now your program has terminated or finished doing the processing. So then it goes to the exit state. So that particular process, or we say the program release to the exit state. That happens when you are in the running state. Because no point going back to the ready state because you are done. Again, there are multiple possibilities. One possibility is program is done. The task is over. Another thing is maybe the user has terminated, exit the program. Another thing is while it is in the running state, the critical error happened. Therefore, you can't proceed it. Always decide, okay, let's exit the program, terminate the program. Again, you can see the three reasons. Program is done, exceptional situation, or user has terminated. So due to any of these reasons, the running state, it will go into the exit state. So exit state is the last state, right? Is it clear up to this point? Because this diagram is super important. Okay. You need to visualize in a practical manner. Right. So then there are some few more states. Another possible state is called block state. Block state. So when the program or the process is in the running state, rather than coming back to the ready state, there's a possibility of always take it to the block state. So in what kind of a situation, the operating system will decide to take the running process to block state. So that happens when there is a user event required. Say now the program has run to a certain level and now user must respond. Enter a particular data, maybe click on OK button or confirm, or user need to select a file or something, right? So until user respond, nothing to process because users will not immediately respond, right? Users will take at least few seconds. Sometimes, right, users don't get the attention that they need to give the attention, right? So therefore, sometimes there will be delays. So therefore, no point taking it to the ready state until this user event happens. Because if it is in the ready state, it will be again given the time slot. So no point giving the time slot until this event is done. So therefore, operating system will take, in that kind of situation, immediately operating system will take that process into block state. Because if operating system knows until the user responds, nothing to do. Nothing to do. So therefore, until the user responds, your process will be in the block state. Okay. Like you just need to confirm. You just need to enter some data and submit. Okay. When the user responds, like user say select OK, user enter the value and say submit. Now your operating system will take that process from block state to the ready state. Ready state. So remember, you come to the block state from running state, but it will never ever directly go to the running state. No, that is not the way operating system work. Now, when that event happen, you are getting back to the bench, waiting bench. So when you get a time slot only, your process will be put it into running. But now you are a candidate for running because your use event is done. So remember, you come to the block state from running, but you don't directly go to the running state. You can only go to the ready state. And when the time slot is available, operating system can take it to the running state because now you are in the ready state again. So that is another possibility. So this is a state transition. All possible state transitions we are looking at. And you must know that it can never go from block to the running. It can never come to the block state from ready. No, those are not happening. Okay. Right. So then there's another thing can happen, which make the state transition a little bit more challenging to understand. That is, there's something called suspended state. Okay, suspended state. So what is the reason for that? Right. So the reason for that is when it comes to your computer, remember you need memory also. We discussed that under hardware. Topic 2, computer architecture. So we have hierarchy of storage. Tertiary storage like CD, DVD, pen drives. Secondary storage like your SSD hard disk. Then your memory RAM include the level 1, level 2, level 3 cache. And then your registry. Remember, your RAM or main memory is limited resource. Of course, anything is limited resource. Okay? But definitely memory is limited. So ideally you may need 60 gigabytes, but you may be having only 8 or 12 GB in the memory. So then your operating system need to use this limited resource in a very efficient manner. So for example, if you look at in my computer, my laptop, if I go to the task manager and go to the performance, you can see that I have only 8 GB memory, which is very minimum. And already my computer has occupied, right, about 6.7. Okay, right, about 6.7. So only about 1 GB is remaining. Right? Right. So this is 8 GB, but effectively 7.7. That means there are corrupted memory cells. So though it says 8, actually my computer has only 7.7 usable memory. And out of that, 6.7 is used. So that means about 1 GB remain, little less than 1 GB. So usually this is the case. Of course, if you have about 12 GB, 16 GB, then things are a little bit better. Okay. Then of course you will be running more programs also. Now in this kind of a situation, your operating system try to do a sort of a trick. That trick is your OS can actually, I explain this under computer architecture. Your operating system can borrow part of your secondary storage, in my case, my SSD, part of it. Maybe it has so much of thing, maybe few gigabytes as an extension to the RAM. But it is not real RAM. Maybe my real RAM is 8 GB, but it can borrow maybe another 4 GB from hard disk or SSD and it look at it as sort of a virtual RAM or virtual memory. So then you always consider it as something like 12 GB, but actually you have only 8 GB. So this is called virtual memory. Virtual memory. But this is not real memory. But your operating system makes sure that your running program see it as a 12 GB now, 12 or whatever. It depends on how much virtual memory you take. So that means it shows, operating system shows the memory bit of exaggerated to the processors, because processors need large amount of memory in general, most of the time. But this is not real memory. Okay. So then what does operating system really do there? So when you're running too much of program, not too much of, say, reasonable number of programs, and when the program demands more memory than physically available RAM, your operating system, what it does is, now remember, different programs are in now your RAM or segments. Part of your OS is occupying big part of your RAM. In my case, part of Zoom is loaded here. Part of Firefox is loaded. Part of PowerPoint is loaded. And say now it is almost full. Now I want to run another program. Say I want to run, say, say, how do you call it? Acrobat Reader. Or I want to run Inkscape. Or I want to run Photoshop. But now almost it is, my memory is occupied. But now my Photoshop also need maybe at least 600 megabyte. What it does is, it take part of this memory from one of the programs or multiple programs, maybe this part, it will copy it to the secondary storage. In my case, SSD. So this part is copied to the secondary storage. It's copy of the memory dump, which is put into the secondary storage. Now this part is available, released to the main memory. Likewise, not only one program, maybe from another program, another part is put it into the secondary storage. So now these parts are free. So my Photoshop can be loaded to these memory address ranges. But so how does operating system decide which programs memory portions will be put in? Usually inactive programs. So that means if you haven't, for example, I haven't given attention to the Firefox for a very long time now, at least for 5 minutes. But actually Firefox is running. Right? So then OS might decide, okay, let's keep part of the Firefox program related memory into the secondary storage or the virtual memory. That is borrowed part from the SSD. And use that free space to load maybe Photoshop. Okay. So that is what is called virtual memory. Virtual memory. Anyway, our next topic is memory management, but there I will not explain this again, okay, because I explain it here. Okay. So if you want to get a feeling about that, if you go to the settings, and search for something like virtual memory. No, not virtual memory. Maybe environmental variable. Right. Say edit the system environmental variable. Okay. Click on that. And there you go to the advanced, and there's something called performance tab. Okay. Performance tab. There you can see visual effect processors, scheduling, memory usage, and virtual memory under advanced tab. So go to the settings and go to the advanced. So then there's something called virtual memory. Okay. So it says a program file in an area on the hard disk. Of course, in my case, it is SSD. Windows use the old terminology in the messages. Hard disk that Windows use as it were RAM. So Windows think it like a RAM, but actually it is not RAM. right? So you can even decide how much. So by default, it has allocated about 14,000 megabyte. Remember, 1048 megabyte means 1 GB. So this is more than 1 GB, about 1.5 GB. So it has borrowed about 1.5 GB from my SSD, right? I can allocate more as well if you need. Okay. Uh, but that is the default value it has taken. So that is virtual memory. Part of the hard disk or the SSD is taken as a sort of extension, but actually it is not memory. It's basically playing a trick. OS play a trick. So again, when you given the attention to say Firefox, now it needs to take it from this virtual memory to the physical memory. Maybe it need to swap. Maybe some other programs memory is now put it into the virtual memory. Or maybe right now the physical memory is available because you have closed some programs. So while your programs are running, right, ready state, running state, block state, and blah blah blah, this can also happen. So what is this? That means say your program is X or your program is PowerPoint, right? So now because now your program may be inactive for some time. Okay, maybe it's in the block state or it is in the ready state, but nothing to run. It's sort of idle now, but a user has not closed the program also. Now, in case of a memory issue, the operating system we can decide, okay, we will take PowerPoint's part of the memory or full memory into this virtual memory or in my case, second SSD. So that happened. Let's assume that happens while your program was in ready state. While your program was in ready state, that happened. So then we say your operating system change the ready state of that process to the ready suspend. It is now suspend because part of the memory is in the virtual memory or the second SSD or secondary storage. It is suspended. Now you can't run that program because not all the memory is in the physical memory. So why do we call it ready suspend? Because you came to the suspend state from the ready state. So if your process is in suspend state, that means at least part of the memory is in the secondary storage or virtual memory. Okay. So then when the memory is again taken back or the program, that memory is again taken, given the physical memory. So that comes back to the ready state. That comes back to the ready state. That means again your program is in memory, RAM. You are back ready to run. Back ready to run. Or sometimes OS will decide to take it to the ready state because the user want the attention. Maybe user try to do something with that program now. So then operating system will take that from ready suspend back to the ready state. That means load it back to the memory. Maybe some other process goes to the ready suspend or some other suspend state because this is for one process, right? So likewise, if there are 10 processors running, there will be 10 process diagrams we can draw. So that process may be in different state right now. Okay. So this is for one process. Right. So this can happen while your process is in the block state also. That means your process is waiting for a user interactions. And because of the memory issue, operating system decides, okay, let's put this into the virtual memory because we need to load another program and we are running out of memory. So then again from block state, it can go to the suspend state. That means part of the content is in the virtual memory. So because it came from block state to the suspend state, we call it block suspend. Block suspend. If it comes from ready suspend. If it comes from block suspend. And now there are two possibilities. One possibility is, now remember, it was in the block state waiting for user interactions, but still the user has not interacted, and operating system has decided to put it into the virtual memory also. That is why it's block suspend. Now there are two possibilities. One possibility is, now because memory is now available, operating system has decided, okay, let's take that back into the memory, that memory, physical memory. That means the physical memory is available, still the user has not responded. But because memory is available, OS can decide, okay, we'll take that part of the memory back from virtual memory to the physical memory. So that means your block suspend state process will come back to the block state. Still, it is block state because now the memory is available, but the user has not responded. So therefore, still you must be in the block state. But there's another possibility. Assume you are in the block suspend. That means while the program was waiting for the user interactions, OS has decided to put you into the virtual memory because of the memory limitation. Still, the memory issue is there. Memory issue is there, so therefore OS cannot take it back to the physical RAM. But the user has responded because remember you came to the block suspend because initially because the user you are waiting for a user interaction. But now user has interacted and given you the say click on the OK button or whatever. But the memory issue is still there. So then it will go from block suspended to ready suspend. Because the user interaction event has occurred, but the memory issue is still there. Memory limitation is still there. So then you always will take it from block suspended to ready suspend. Right? And when the memory is available, OS will take it from ready suspend to ready. And of course, then there's a possibility of it getting the context time slots and getting it to this loop again. And maybe finish or release. So this is the big picture. So you must be very, very, very sure of what is this. So what are the possible paths? Why a particular process goes from one state to the other? And these arrows are very important. Remember, this is one directional, unidirectional. This is unidirectional. But these are bidirectional. This is unidirectional. This is unidirectional. This is unidirectional. So these directions are very important. You can't just draw something. You can't just draw a line like this. So you must show whether it's bidirectional. If it is bidirectional, you can draw like this also, or you can just draw it like this and then. Okay. So do you have any question about this? Because this is the most important thing. Now you are pretty much done with process management. Any question? Anything not clear? So can you explain each and everything, every bit of this process transition? New, ready, running, blocked, block suspend, ready suspend, and now for the exit. So you must remember these state names and these event names. If you can remember, it's better to remember the event names also, like admit, dispatch, release, timeout, event wait, event occur, right? Suspend, activate, event occur, right? But you must, if they ask you to draw this diagram, you must give these names properly. And it's always good to give these event names also and make sure you serious about these arrows, right? Whether it's bidirectional or unidirectional. Right? So you go to the exam to pass it, right? With good results. No, you don't go there you don't go anywhere to fail, right? So don't collect failures for your life. Have high standards. Okay. So new state, the user always has run the program, however, not yet admit to the ready state. Ready state, the process is in the ready queue, waiting for running time slot or waiting for the context. Running, the OS has given you the attention. So that process is being executed by the processor right now. But that will be a very small time period. exit, the program has either terminated naturally, or user has exit, or due to exception or error, OS has terminated. Blocked, waiting for user interactions. Block suspend, while waiting for the user interactions, it has taken to the virtual memory. So therefore, OS has put it into the block suspend. Ready suspend, while your process was in the ready state, waiting for the time slots due to memory issue, OS has taken at least part of the memory of that process into the virtual memory. So therefore, now we are in the ready suspend. And remember, while you are in the block suspend, you can again go back to the block, or you can go to the ready suspend. From ready suspend, you can come back to the ready. Okay. Not suspect. Suspect කියන්නේ සැක කරනවා. මේ suspend. Okay. Right. So suspend කරනවා කියන කොහොමද? somebody යුනිවර්සිටි වල ස්ටුඩන්ට් ලා එහෙම සස්පෙන්ඩ් කරන්නේ පන්ති තහනම් කරන්නේ. සස්පෙන්ඩ් කියන්නේ යාට ඇක්ටිව් වෙන්න බෑ. Right. So question. Block suspend, ready suspend. Can you please explain again? Right. Block suspend and ready suspend. Right. So first of all, you must understand what is virtual memory and why do we need virtual memory to understand ready suspend and block suspend. So I told you that your programs must be in the memory because your processor will always access the RAM. Processor will never ever access secondary storage directly. That is the first thing you need to understand. Your microprocessor will never ever access your hard disk or SSD or secondary storage. It only communicates with memory. So therefore, if when a program is running, that part of the entire program or part of that running parts must be in the memory. It doesn't mean that memory is running the program. No, memory is just a storage, but your OS will only access RAM. Now, there are situations your memory is running out. Say you have 8 GB, but already more than 7 GB is used, and you try to run more programs. So then when programs competing for the memory, OS has to put some of the memory, like a snapshot of the memory into the secondary storage. So that is not your normal hard disk areas. It's also part of your SSD or hard disk, which is separately allocated. Okay. And take a sort of a snapshot of this and put it into, say, your SSD. So when that happens, because that memory is now memory snapshot, values of the memories or memory dump is now in your secondary store. So when that happens, your operating system cannot run that process because part of the memory related to that process is in the secondary store. That is where if you are in the ready state, if that process was in the ready state, the moment that is put it into the secondary storage, your operating system will put that process state for that particular process from ready to ready suspend. But by the time if that particular process was in a block state waiting for user interactions, then it will consider it as block suspend. That means now it is part of the memories in the secondary storage and also waiting for the user interactions. If the user interact, it will come back to it will go to the ready suspend because still it's in the virtual memory. But if the virtual memory issue is resolved, but still the user has not interacted, so then it will come back to the block state. And while you were in the ready state, once the memory is available or OS decided to take you back to the memory, you are coming to the ready state. While you are in the ready state only, you can go to the running state and come back. Processing can happen only while you are in the ready state. So therefore, if you go to these states, you must come back to ready state so that now you are again candidate for running. Okay. Is it clear? Or if you have very specific question, I can answer now because I explain it in general. If you have very specific question saying I can't understand this particular thing, I can explain it. Okay. And think about it. It won't. Sometimes you need bit of time, bit of thinking, right? Doing bit of past paper questions and so on to better understand, right? But your understanding will be improved the more you think about it, the more you do some questions and so on. Okay, right. So I explained the block state, waiting for the user interactions, block suspend while you are waiting, while your process waiting for the user interactions, it has been taken to the virtual memory. Ready suspend while the process was in the ready state waiting for the running, because of the memory issue, it has that process or that program has taken part of that program has been put it into the virtual memory. So therefore, OS has put it into the ready suspend. Okay, right. So we take a small break. After the break, we'll continue our discussion on process scheduling. Okay, right. So now 5:06, we will start at 5:10. So now the bulk of the task is done. So therefore, possibly we can finish it today itself. Okay, we'll see. Anyway, we are not at all hurry because we are on target. Okay, right. We'll start at 5:10. Okay, so let's continue. Right. So now you know how the processes are handled by the computer or the operating system, right? Multitasking. Multiple processes seems like running parallelly, but in reality, the time slots are given, right? So you can think of this happens in a one physical processor or one particular core. Of course, different cores, there will be parallel processing happening, right? So you don't need to worry about how the different processors, different cores are parallelly working, but you must concentrate on a single core, how the multiprocessing is happening, okay, or single processor, right? So remember, there are a lot of decisions to be taken, right? So if you look at this diagram, so there are so many possibilities, right? So therefore, this is not done by one particular scheduler. So schedulers are also programs or sub-programs in operating system, because operating system need to do so many things. So operating system has sub-programs. So remember, operating system also running processors, okay, to do the operating system related tasks. So there are multiple scheduler processors that keep track of different aspect of this diagram, because one processor cannot keep track of all these things for multiple processors. So therefore, there are different processor schedulers that take care of different type of transitions. Okay, different type of transition. So let's see what are those schedulers. All are under operating system. Okay, so we call them process schedulers. So process schedulers task is give each and every process a fair attention, and also it must honor priorities. If a particular process has high priority, the scheduler will give uh, more attention, more time slots, more opportunities. Okay, but in general, it will try to be fair. Okay, and give a good experience to the user. So the user must feel like all the processes are sort of running. So again, it is not equal attention. So some processes need more attention because they are heavily process oriented. Some processors need little bit less attention. Still, you will end users will feel like all these things are happening. Okay? Right. So this is where you can see the different process states and so on. You can change the priority. I already explained. Okay. I already explained. Right. So as I told you, the process scheduling is done by not one scheduler program, by three scheduler programs. What are those three schedulers? We call them long-term scheduler, short-term scheduler, medium-term scheduler. So that means these process state transitions are done by three schedulers in the OS rather than one scheduler. Right. So what are those three schedulers? Long-term scheduler, short-term scheduler, medium-term scheduler. So long-term scheduler will manage admitting processors. So that means this particular thing. So this is from our full diagram. So when to admit a new process to the ready state is determined by long-term scheduler. That's it. That scheduler's task is make sure when there's a new process in new state, and when it has a reasonable number of ready processors, it's not very or too busy, it will decide when to take that new process into the ready state. But it will never go back to the new state, right? So that is what long-term scheduler is doing. Its only task is when you have enough resources, enough, not too much programs are running, take that new process into the ready state. Okay, that's it. So then this is done by another scheduler. Okay, right, that is called long-term scheduler. It's very easy. Right, so then we have the second scheduler, short-term scheduler. So short-term scheduler's task is take your ready state into running and take running state into ready when time pass. So that is ready to running. So that is the most important scheduler because this is what happens most of the time. Taking ready to running and when the time slot is over, taking back into the ready. So this is the medium term scheduler. Sorry, short term scheduler. And short term scheduler. So the medium term scheduler manage the suspend situations. So suspend situation is when the program is in the virtual memory. Okay. So when to take a process to the suspend? Of course, there are two possibilities: ready to the suspend and block to the suspend. And when to take it back to the ready or block state. So those are done by medium term scheduler, right? Anyway, that is just three schedulers doing different tasks. Okay, three different aspect of transitions: long-term scheduler, short-term scheduler, medium-term scheduler. Right. So now we move on to another subtopic, another very important subtopic where examiner has in A level they have checked this whether you know this. Process control block, PCB. So remember in file handling, last week we discussed something called file control block, FCB. So FCB is a data structure managed by operating system to keep summary of each and every file. For each file, there's a file control block. So it has a file name, file size, file extension, security related things, access related things like file owner and so on. If the file is used by other programs, which processors are using right now, to which point it has been read, what is the next bit of data to be read. So all these data is in the file control block that is related to the file management. So this is called process control block. And this is related to process management. So remember process can be in different state: new, ready, running, exit, suspended, sorry, blocked, ready suspended, block suspended. Okay. And again, they can go from one state to the other. And remember here also ready to run to ready. You keep coming sometimes maybe within 1 minute, this transition can happen 10 times for one process. Of course, the other processes are also going through this. So when a program is coming from running state to ready state, that means it has temporarily stopped the running. So when program coming from running state to the ready state, that means it has temporarily stopped running that program. So when the time slot is again given, again you must start from that point onwards. So this running is done by processor, right? Your data is in registries, your instruction is also in the instruction registry, and the instruction is taken to the arithmetic and logic unit. The relevant control signals are sent, relevant data is loaded to the ALU and getting processed. So there's the next instruction, next instruction. Maybe during the current time slot, current context, in your machine code, maybe 100 instructions were executed. but that is still your program is running. Now your time is over, time slot is over. Maybe OS has decided, okay, let's put it back to the ready so that we can take a different process and give the attention. So now what happens? Now it has executed, say, another 100 instructions, another thousands of instructions are waiting to be executed. Now, before it's taken from running to the ready, the current situation must be written, kept, saved, so that when it is taken back to the running state later, you can start from that point. So remember, context switching is good because multiple programs seems like running, but at the same time, there's overhead. So overhead is whenever you stop giving attention to a process, you need to save the current situation so that you can resume later. That is additional burden. So every time program going from running to the ready, the current situation is written to a data structure called process control block. And every running process has a PCB. If there are 25 programs running, processors running, there are 25 PCBs managed by OS. And each PCB has the current situation. So usually PCB is updated when program goes from running to the ready or to any other situation. Right? It is not getting updated all the time. When there's a state transition, the PCB for that process will update. PCB for that process will update. So especially when it going from ready running to ready, it needs to write down all the values of the current registries because it must be reinitialized so that it can process from that point. What is the current execution instructions memory address? What are the currently open file names? All these things must be needed so that you can again, when you take it back from ready to the running, again it will read the PCB because you have already saved it when you are going from running to ready. Now you read the PCB and reinitialize the ALU with the registries and so on. And then only to execute from that instruction onwards. Maybe another about 200, 400 instructions will be executed in that time slot. Or maybe now your program terminated, fully finished during that slot. All the other things were done. And then you can go to the exit state. Of course, if it is exit, no need to keep the PCB, process control block, because you are done. So then that PCB will be deleted, release, right? So is it clear? First of all, you must know why PCB is there. So the PCB keep track of the current situation of the process. And every time there's a state transition, the PCB will be updated. So the PCB will have the last execution situations, registry values, what is the last executed instructions, and anything related to running the program, like open files and so on. And it's a data structure managed by OS for each and every process. And when it is coming back to the run state, it will read those values and restore the hardware, like registries and so on, so that it can resume the processing again for that time slot. Okay. Right, so that is called PCB. So if there are 10 running processors, there are 10 PCBs managed by OS. Okay. So these are the typical things. So every process has a process number or the process ID. And you can see that even when you go to the task manager, right? Process number is there. PID, process ID. You can see PID. So PID 0 is the system idle process. So that is the first process. So then Zoom has, in my case, 13,100 and so on. So different processors are given different IDs. So obviously process ID is used to identify the process control block. Okay. Okay, I close that. Right. So process ID is there. Process state. Is it now in running state, ready state, suspended, block suspended, ready suspended, or even new state? So the program counter is what is the currently executed instruction so that it can start from that instruction onwards. Registry values during the last running situation so that it can be restored. So the memory ranges allocated for that process so that it knows it can access only these memory ranges, and list of open files by this process and so on. Okay. And anything else that OS need to resume the process. It depends on exact OS. Right? So, but these are the general things that your process control block will have. Okay. Right. So now we can subdivide or classify processors. Classify processors. We do two classifications. So remember, this is our second day, right? Second day or third day? Yeah, second day. So next week, next class, we will finish it, the entire OS. Okay. Right. So this is our first classification. We can classify processors for process means running programs into two categories. One is CPU bound processors. Other category is IO bound processors. Again, there are no hard and fast rules and say from left hand side we have CPU bound and from this line right hand side we have the IO bound. There can be some gray areas as well. Some processors can be somewhat CPU and IO and so on. Okay. But in general, CPU bound means that processor need a lot of processor attention. It's process intensive thing. A lot of calculations and so on is there. Right? So then we call it CPU bound process. Like a lot of calculations and so on. Right. But some processors, process means running program, it needs a lot of reading to reading from files, writing to files, database interactions. So a lot of data oriented things. So data oriented means you need to communicate a lot with a lot of IO, input output, or sometimes interactions with the user. So those are less processor intensive, more customer or the end user interactions, file interactions, and so on. Anyway, this is just a classification, right? Just a classification. So usually CPU bound processors need more processor attention. IO bound processors need less processor attention and more user attentions and other hardware level accesses like disk. Right. So that is one classification. But there can be some programs which need a lot of CPU attention and IO bound attentions. Okay. Right. So this is another classification. So this classification is more important. This is a technical classification. So that is, this is not actually the processing or the processor classification, rather how your OS schedule it or how your OS run processors. Right? So there are some process OSs which are preemptive context switching. Some OSs prefer to do non-preemptive context switching. And most of the time, the operating systems use mixture of these. For some processors, it use preemptive. For some other processors, it give non-preemptive switching. Okay. So therefore, again, you can draw a line and say these OSs are preemptive, these OSs are non-preemptive. And most of the time, modern OSs treat some processors in preemptive manner and some other processors in non-preemptive manner. It depends on the programs and so on. Okay. But if it is a real-time operating system, remember the real-time OSs like missile guide systems and so on. Those are always non-preemptive. Non-preemptive. But general purpose OSs like our laptop, smartphones use, so they are more into the preemptive. But sometimes they also can act or work, operate on non-preemptive mode for certain tasks. Right. What is mean by preemptive processing or scheduling? Preemptive scheduling means your processors or running programs are given fixed time slots. And at the end of that time slot, it is taken back to the ready state and another process is given the opportunity to run. Those are fixed time slots. Fixed or fairly fixed. But depending on the priority, a particular process may get more time slots, more attention than other times processes. But what you get is a sort of a fixed time slot, maybe 10 milliseconds. So then attention is given to another process. But if it is non-preemptive, when a processor always give attention to a particular process, it let it finish, complete the task. Or due to error, it terminate, or else it will let it happen, finish it. Okay. Or it will let it run until there's a waiting situation like user input and so on. Because if there's a user input or user interactions, uh, anyway, it will attention will be given to another process because otherwise you are wasting the computing resources. But in general, when a process is selected for running, as long as it runs, you always will let it finish it if it is non-preemptive. But again, in reality, most of the time, OSs prefer preemptive, non-preemptive, giving opportunity for each and every process. Or sometimes it's a mixture of scheduling. Okay. So if it is preemptive, there's more overhead because there's a frequent context switching. For non-preemptive, less overhead because you don't need to keep saving the current situations and again reading and blah blah blah. Because when a process is given the time slot, it can finish. It can OS will let it finish it. Maybe it will take 2 seconds, but it will let it happen, finish it, and then give attention to another process and let it finish and so on. Okay. But in practice, mostly OSs are preemptive. But it doesn't mean that it's 100% preemptive or 100% fair. It may give more time slots to some processors, and of course, you can, for example, I don't know whether you saw this when you go to the task manager and details. So if you right click, say zoom or whatever, so there's an option in set priority real time. So real time means you make that you ask the OS give this program right finish the task. Let this program finish the task. So that means when you say real time, it's pretty much we are asking it consider this program or running process as non-preemptive scheduling. Non-preemptive scheduling. Okay. But again, it is not 100% because something like Zoom will then keep running forever, right? For hours, not letting others to run. But it will try to give reasonable amount of time to finish it. Especially if it is a small task, then it will finish it also. The real time means let it act for that particular process, act like non-preemptive scheduling. Okay, right. So we already discussed about this, right? So far we thought that our processor is single processor, single core. But I told you, then of course, how do we do multitasking? Context switching. But I told you that at this while context switching is used to do multitasking or at least pseudo multitasking, we can or the computer OS can utilize if there's a multiprocessors, there are multi-cores in your processor, and of course multi-threading. Okay. So as I explained, you multi-processor means you have physically more than one processor. That means in the motherboard there are two processor slots, and you fix two processors. So usually that is when you use when you run servers, very high-end servers. And each processor has its own L1 and L2 cache, but the common L3 cache. So then, of course, we have another way of parallel processing, multiprocessing, because maybe one program is handled by one processor, other program is handled by one processor, or maybe set of programs are handled by this, another set of programs are handled by this. And in that processor, of course, still context switching will be used. Context switching will be used because you don't only run two programs in a computer, right? And then multi-core. So multi-core means in your single processor, but physically in the single chip, physically you have multiple cores, like physical cores, but one chip. So then we say multi-core. So you can have single processor multi-core or multi-processor multi-core. Okay. So then each core can run different programs. This core is running process one, this core is running process two. So this core is running process 135, this core is running process 246. And multi-threading means a program can be considered as multiple sub-threads. So that gives you another parallel processing opportunity, multi-threads. Especially your browsers heavily use this. That is why browsers take a lot of resources. So again, if you go to the task manager and go to the processors, say something like Firefox, that's Firefox. Okay, let's change it to the name. Right. So you can see there are so many sub-processors. Right. So those are mainly multi-threading. Sometimes for one tab. So usually for each tab, we take one process. Okay. But if you close these things, and let's open it again. Now Firefox has only it's vanished. So Firefox is not now running process. Okay, because it exit. You can see now Firefox is not there, obviously. Right? But if I start Firefox again, okay, right. So now we can see all of a sudden not one process. Yes, one big process, but multiple threads are running. That is to get more attention. So processor, your file browser try to make it fast as possible because there's a competition between the browsers also. But the bad news is browsers tend to take too much of your resources. Right? So same is done by the edge. Okay, edge. So they try to get as much as possible attention, resources, so that users feel like this browser is very fast. But sometimes they do it in a very unfair level as well, so that other programs become slow. Okay? Right, so that is called multi-threading. Right. So then our final concept is parallel computing versus distributed computing. So this is also related to processing. Okay? Processing. Right. What is mean by parallel computing? So parallel computing means you have multiprocessors, same memory, RAM, but you have multiple processors and multiple processors running either multiple programs or different part of the same program also. Okay. So that is called parallel computing. Because in the same memory, these processors can exchange data between the processors. Okay. But it's the same hardware. It's localized. It's the same computer, same place, same hardware, but you have multiple processors in the motherboard. So that is called parallel computing. Then what about the distributed computing? So distributed computing means you have different machines, different hardware computers with its own processor and memory. And usually a program is executed with one computer, but there can be situations where a particular program is executed with the collaboration of multiple computers. Sometimes those computers are in different parts of the world, maybe connected through internet. Right? So then someone will ask, why do you want multiple computers in different parts of the world doing the processing of one particular program, one particular task? So the simple answer is, of course, yes, those are very rare, but there are such kind of highly process intensive activities for research purposes and some special activities like Bitcoin mining, highly process intensive. Sometimes different machines can collaborate to do that fast. And there are some scientific calculations, research oriented calculations. Sometimes it takes days to do the calculation, days, or sometimes even weeks for a single machine. So then it can, of course, you need to give the permissions and so on. So then if you go for the distributed computing and the relevant access is given to that program or process, then it will be different part of the program is executed by different machines. And so very good example is, for example, now at the end of this session, or maybe sometimes tomorrow, sometimes even few days later, I upload the recording to the Google YouTube. So when I upload, it's about 400 megabyte, 2 hours of recording. So it take about at least 30 minutes to process. So the moment I upload it, it is not available to you guys or to anyone, right? So there will be message saying if someone access that URL, this video is still being processed because it's a heavy processing load is there. Even in your now the moment my your session is over, when I stop the session, uh, there's a window because start I have started recording in my laptop. Your recordings are saved in my laptop. So whatever I'm talking and the screen share things are also right now getting stored. Okay, so to a file. Right? I will show you the file also. So these are the recordings of each and every session. Even your past sessions are there. Okay, and right now this is your session. Yeah. This is your session, 26 February. And if you go there, you can see this is getting still, it says 0 kilobyte, but actually this is now getting saved. Okay, getting saved. The moment I stop your session, it start processing because it is not saved as MP4 file. Rather, it is saved as a very compressed file, because otherwise it takes a lot of resources while the Zoom session is there. So therefore, the moment I stop your session, it start converting that video into MP4. It take at least about 20 minutes. You can see to do that processing, my laptop take about 20 minutes. It's heavily process intensive. But if I have multiple laptops with me, maybe 3 or 4 laptops, and if I can set it as a distributed computing problem, so then maybe first half an hour is processed by conversion is done by my laptop. The next half an hour is converted by second laptop, third laptop. And maybe within 10 minutes or 5 minutes, each computer has converted its allocated portion, and then those portions are, because you need to connect them to the network, then those portions are combined together within few seconds. So that now the earlier it take 20 minutes, but now maybe we can do it in 5 minutes, because 4 computers are working on that process, different part of it. So the YouTube definitely doing that. So when we upload a video to the YouTube, definitely it is not one server, multiple servers process, and multiple servers process it, and still it takes sometimes, right, 30 minutes. Okay, because its conversion is much more sophisticated conversion, so that it's YouTube friendly. So in that kind of situations, we use distributed computing, right? Video processing, some heavily computing oriented problem solving, Bitcoin mining. So this kind of distributed computing is used, or especially in servers like web servers, database servers, we use parallel computing. So parallel computing and distributed computing are two different things. And sometimes each node of the parallel computing is all using each node of distributed computing may be used parallel computing. So that is also possible. That means high level distributed computing, but each node or some nodes use parallel computing also. So likewise, there can be so many possibilities, right? Right. Any questions? Any questions? Because so you must have better understanding of how the computer work at the end of this session. Right. So we'll do few past paper questions. Few. Right. So this is 2023 paper. MCQ question. Question 5. Which of the following will cause the CPU to execute a different set of instructions? Right. Different set of instructions. Context switch, interrupt, user select in the shutdown option in the computer. What is your answer? Now, the set of instructions are getting executed by your computer processor under the control of OS. Now, which of these will make it different set of instruction? That means different process is now running after that point. So this process is not no longer running. Now different process is running. That is what is my different set of instructions. So which of these activities can cause that? That is basically a context switch. Obviously, right? Anyway, what is your answer? What is your answer? Context switch, interrupt, user select in the shutdown option in the computer. Anyone? So you need to understand sort of to the perfection to answer these kind of questions. Sometimes you feel like you have understood, but actually you have not understood well enough. So that is a trap. Sometimes you have not thought seriously in some special cases. Maybe you have only understood the general cases. Remember, operating system is also a process or set of processors. Because operating system is also software. So when you say shutdown, it's OS must run another process, shutdown process. and shutdown process. So the anyone want to give answer? Don't worry. If it is wrong, that is fine, right? You are not going for the exams in 1 month time, right? You have one more year. Right. Obviously, when we do context switching, that is giving attention to a different process. So then, of course, different set of instructions must be run. So from the last executed point, it will read the PCB of that process and initialize the registries and so on and execute from that point on. So then again, when there's a context switch, again, a different process will be initialized and execute from that point, right? Using the PCB. So therefore, A is correct, right? So when there's a context switch, a different set of instructions must be executed. So what happens when there's an interruption? So interruption means your currently running process is interrupted due to some reason, maybe error, exception, or high priority program that need real time attention, try to get the process attention. Okay. So then again, a different type of program can run, right? Or OS will select, it depends on which reason, but again, different set of instructions will be executed. And when the user select to shut down, so remember, shutdown is also a process. So all of a sudden, you can't say shutdown. Shutdown must happen. It's running a process in the Windows. Windows has so many processes. So therefore, when you say shutdown, of course, OS will give you some warnings and ask you to save when you are running files and so on. But if you say, okay, shutdown, so then shutdown process is running. So that is again running instructions. Shutting down is also a program. So I'll go forward. In any of the situations, uh, different set of instructions will be executed. Right, 5. Right, do this one, 2020 MCQ Let 13. Again, you must have understood from right top to bottom, 1 to Z, A to Z to answer these questions. That means you have serious understanding, not understanding in the surface level. So that means you are a serious person. You think in depth. When the number of processors started by a user on a single processor computer increases, that means now a lot of running programs are running, a lot of running processors are there. What happened to the response time of each process as perceived by the user? That means as the user feel. Okay. So now how the user will feel like the response time of the programs and the memory management related work of the operating system respectively. So one part is how it is felt by the end user. Now the end user is keep running more and more programs. Second part is how does the memory management unit feeling about it? Of course, more and more programs are running from means more and more programs are loaded to the memory. Now the memory OS might or the computer is running out of memory. So now the OS has a headache. How do I manage this limited memory with these so many processors? So that means it has to take more and more things into the virtual memory, because it's struggling now. And sometimes again take back from virtual memory to the physical memory. In order to do that, some other thing you need to copy to the physical virtual memory or the secondary storage and so on, right? Right. So the first one, both the response time and memory management related work increases. Is it correct? Definitely response time increases, right? Because now more and more programs are running means you feel like it's getting slowed down. Because if 20 programs are running earlier and now 50 programs are running, you feel like response time is less. Things are getting slowed down because so many things are happening now. And of course, memory management related work increase because the memory need, you always need to keep right doing stepping, putting memory. pages into the secondary storage, taking back again, again putting back something else. Sometimes it's so busy with hard disk or your SSD doing memory swapping. So this is yes. Response time decreases. Response time decrease means it happened quickly, right? Response time, yeah, decrease means good. While the memory management related work increase, no, response time will not decrease. Response time will increase. Response time will increase, yes, while the memory management related work decrease. No, that is also increase. But this part is correct, but this part is wrong. Both the response time and memory management work decrease. No, there's no change to either of them. No, there's a difference. So I'll go for one. Response time increase. Response time increase means it take more time to response. And memory management related work increase. I'll go for one. Okay. Right. 2021 MCQ question number 10. Right. So this is a process transition diagram for a particular process. Okay. Right. Read the question. Don't worry, there are so many other questions for you to do. You have the past papers. Amara logs into a single processor computer. That is to make your life easy. Right? So then you don't need to think too many things. It's a very basic single processor innocent computer. Amara logs into a single processor computer and start a program to work on his presentation, like PowerPoint. He opens up a web browser. Now the second program is also running, web browser, like Firefox. Two, to get some information as well. Now two processors are running in single processor computer. At least two processors, right? Of course, there can be OS related processors and other background processors running. But at least these two processors are now running. Consider the following process state diagram with respect to the process corresponding to Amara's presentation program. This is related to presentation or something like PowerPoint. So similar thing will be there for uh, web browser and of course any other running. Okay. Right. Consider some reasons for about state transitions. Which of the following gives correct combination of reasons for transitions A to D? A to D. What is A to D? That is A, B, C, D. Right, A to D. So you must say what is A, what is the reason for A, what is the reason for B, what is the reason for C, what is the reason for D. Right? Right, do it. Do it. So you, when you attend a session, you finish it, okay? Then you are relaxed. Do you do other things in your other times, right? Don't think about ICT all the time. Maybe another 2 hours per week. Other times you enjoy your life. Life is not all about doing A-level. But when you spend time for a particular thing, maybe make sure that it's very productive, high quality, 100% attention. So then you don't need to think about it all the time, right? So what is your answer? Amara saving his presentation on the hard disk. So that is input output related things, right? Remember either user attention or file input output. So during that period, usually it should go from running to block because saving. So we'll see if you have better answers, we'll find. But probably this is the running to block. Operating system scheduling the presentation process to run on the processor. Now it has scheduled to run. So that means ready to running. This is a operating system suspending the presentation process to let the web browser process to run on the So that means you are suspending means you are taking that back to the ready so that the web browser program can be taken to run. So suspend. So remember this is called suspending. So therefore this is B, taking running to ready. The finishing of the saving the presentation on the hard disk. So it has now finished. So it has now finishing has, so the saving has finished. That means input output operation is now done. Now it should be back ready for the running because in block situation is now over. So remember either user interactions or file interactions or any other input output interactions like printer. Now it is done. File interaction is done. So now it will go from block to ready, that is C. So therefore 1D, 2A, okay. In other words, A2, B3, C4, D1. So answer is second one. Answer is second. Right, so this one is easy. Right, take your time and do it quickly. Take 1 minute. Okay, so what is the answer? Program in execution in a computer is called a process. Which of the following is possible state transition sequence of such a process? Possible. Yes, it can go from new to ready. It can go from ready to running. And from running, it can go to terminated. That is possible, right? So it cannot go from block to terminated directly. No way. From block, you must come back to ready. Okay. You can't directly go to terminated. So from ready, new to ready, you can. Right? From ready to block, no. It is running to block. Right? So you can't go from ready to block. While you are running only, you can go into block. This is not possible. New to running, no, you can't go from new to running. So you must come to the ready and go to running. So this is not possible. From new, you can't go to the blocked. So therefore, answer is what? Answer is 1. Right? Answer is 1. Right? What about this? A program in execution in a computer is called process. Such process transit between several states during its lifetime. Which of the following correctly represents a possible state transition sequence? Again, similar question. Now you should be able to do it without any issue. What is the possibility? Now think about the impossible thing. So invalid possibilities. And the moment you find invalid scenario, you take it out. What is the answer? So you must remember the process diagram now. So that is obviously all new. That is fine. So there's no way you go from new to running, right? It must come to the running ready. So therefore, these are all wrong. New to waiting, there's no possibility. And from ready to waiting, that is not possible. So therefore, new to ready, ready to running, From running, you can go to waiting, right? From waiting, you can go to ready. That means that event has happened. From ready again, you can go to running, and from running, you can go to terminate. So again, the answer is 1. Right, that's it. Right, so now we have done 2 topics in OS. So the last topic is memory management. So remember, memory management is considered by IT, A-level ICT students as one of the most difficult topic. So there are such things, junctions. One is memory management. Another one is some people students think representing data in computer is difficult. This is another thing. Another thing is I always keep telling this. Another place is subnet mask and compute calculations in network. Right? Another place is database normalization. So those are the sort of students consider as difficult. And memory management, lot of students consider that it is the most difficult part. If not, subnet calculations. Okay, so therefore make sure better you read the note before the next session. So the memory management note, because you need to be very serious to understand that. Okay, right. We stop at this point. Thank you.